So where we are responsible?
End of last week. This is not included. Okay. So you don't have to memorize a lot of things. Okay, I will go over again. You don't have to memorize a lot of things, and I will. If there is a formula that you need to know, I will give it to you. Okay, so you don't have to. You need to know what the cost function looks like. You need to be able to write a cost function, but if you but you don't have to remember the Riccati equation. You don't have to remember. I don't know the optimization, Hamiltonians, and all that stuff. You know how do you optimize? What are the for rules and things like that? You don't have to do that.
And
if you, if you know the if you want to use Bascura, then you have to memorize that. It's not too much. It's just one simple formula.
No, but the derivation.
No, derivation. I'll make you ask derivations. But you need to understand where things are coming from. That's a recommendation. I might ask a derivation, but it will not be something that you should be memorized. I will not tell you memorize the proof that we did in the class and redo it again. And someone memorizes it and gets perfect form. If I ask something to prove, then it will be something new. Then you need to understand where things are coming from. It will not be very difficult. I don't do that too much. I just want you to understand where things are coming. I might be asking questions about LQR. What do you need to do in order to do that? Or design an LQR controller for a 2x2 and do it intelligently and tell me at each step how you did it. So I can see if you understood the concept or if you did it. You know, that kind of thing. What's that? I looked at the first midterm, sort of didn't finish it, but overall the class did fine. Okay, so you're doing good. And I think the second midterm will be of the same nature, and I promise you will get your midterms before the final, so you know your grades.
And what about the Liapanov syllabus?
We have to do it on Wednesday. Okay, we have to do it on Wednesday, and that's why I think I'll need 2 Wednesdays. Okay, so this Wednesday we might do Liapanov, and then we might look at the project, or vice versa, whichever comes first. But in terms of Liapanov is a different topic, really. It is nonlinear systems. Okay, it is not very well connected to this. It's just maybe it shouldn't be in this class. You know, I think it should not really be in this class. It is a separate topic. It's about nonlinear systems. It's about giving you perspective on things. In terms of controller design, we are done. This is the end of it. Okay, we have taught all the material for controllers. So you can do your project and everything. So Lyapunov will be something extra that I want to show you. Alright? And maybe I do it this Wednesday. And the next Wednesday I'll do controller designs. So today we will do also this evaluation form, which will be in 10 minutes or so. So in those 10 minutes, I want to show you quickly what a controller is that on that instrument, so you have some idea of how I do it. Okay? So let's do that. I apologize for this, but I think someone is just hitting this and it's going up. I don't know what's. Okay, so let's concentrate on this one. So this was the controller that I did last Wednesday. Okay, so we have the state space model. This was for lateral dynamics of an airplane, 4x4, right? And then we did a stabilization loop that we designed using LQR, right? And then we chose, I think that was the angle, right? It was angle in radians. So we chose that and we did an outer loop to that. And then we had a gain over here, okay? And then we gave a step input of 0.6, I remember. And then we looked at the result, okay? That's what we did. So it's still here. So, and what I did here in this class now, I replaced this with a command filter over here, and we'll see what happens with that. Alright? So, let's start with this. Let's see what will happen. I say run. So it's done. So the step input is here. See the final values, you can maybe see it is 0.6. It starts at the step time is 5. Then the result for the angle for a field looks like that. So it goes up, here you have some sort of calculation. 0.6 goes back over here, you have a steady state error of 0.1. This is 0.5 here, and this is 0.6, so you do have a steady state error, right? And remember when I did this with the integral controller, it got a lot better. But you see that overshoot, right? And you see that oscillation, and you see this kind of ugly thing. So, but the reason is really that you have a step input over here, right? It's like a step input, and it overshoots, of course. Instead of the step input, if you would give a smooth input, it will look different. And this is, I just copied this thing exactly to this side, and here you have the same thing with a transfer function, which is indeed a first order low pass filter. In fact, you know, I have 0.1 divided by S 0.1, so it's like this, 0.1 S plus 0.1. So this is equal to input versus output. So it would be S times X plus 0.1 times X is equal to 0.1 times Y. So it would be, if you take the Sx is equal to minus 0.1x plus 0.1 y. So it would be x dot is equal to minus 0.1x plus 0.1 y. So this is what I have over here. Right? 0.1, I'll talk about this one here. Okay, that's the reference command. 0.1 divided by s plus 0.1, x divided by y is the input, x is the output. Okay, you do the multiplication, you get x dot is equal to minus 0.1x plus 0.1y. So this is the first order type of filter that I have. So I'm choosing what has been chosen is that I have 0.1 is chosen and this 0.1 is chosen. Okay? And this is the A and B that you need to choose that I was telling you about. It's over here. Right? It's A and B, first order. I chose 0.1 for whatever it is. Okay? So let me put a scope to this, copy it. Let's put the scope to the output of the reference filter as well. And maybe this one I just removed. Okay? So, same problem. I will just run. All feedback gains are the same. The K, the minus 8, everything is the same. I say run. And make sure that the step input is the same. It's at the fifth second, it's 0.6. You see, it's exactly the same. You say run. And look at the output. Still goes to 0.5, but a lot smoother. There's no overshoot, nothing. It's the exact same controller. All I did was I manipulated the input to the system. You see? Let's look at the input. The input is still a step input, right? Still a step input. However, the output that comes out of the filter that goes actually into the controller looks like that. See, in fact, it goes to 0.6.
but it goes smoothly as a first order response. Okay? So the actual input is 0.6, it was a step input, but I smoothed it out. Still goes to 0.6. The result is a smooth output, but still the steady state error is the same. But it's still without any signal. You see what it's doing? So if you could plot, I don't want to spend time on this now, but if you can plot this and this on top of each other, you will see what I have been plotting. You would see the step input and you would see the smooth input both going to 0.6. Okay? Once again, here is the step input that I have given. Goes to 0.6. It's a step input at 0.5, at the time equals 5. And this is the response. At 0.5, it starts going up slowly, and it reaches that point in about 60 seconds, the steady state. And let's look at the response, and this is the response. It starts at 0.5, goes to 0.5, and reaches the steady state again approximately around 40-50 seconds. So it's kind of trying to follow this one, right? And this is why we call this a model following control. All right? So now we also had the same thing, the same problem without the command filter. We did this last time with an integral controller, remember? So I think the step input was the same, 0.6. And we ran that already. And let's see what the output here is. The output here, it actually goes perfectly to 0.6, but in a much faster time. Look, it goes there, it's a much steeper time here. And in about 35-40 seconds, it kind of reaches the steady state. Now what I can do now is I can take that, I can take this command filter, copy, and put it over here instead of that step input. Good. Okay. Now we have the exact same thing with that command filter. Say run. So it's about the same, but it's supposed to follow this one here. Okay. You can make the command filter a bit faster. How do you make the command filter faster? Let's go back to this one. Maybe this is easier. How do you make the command filter faster looking at this equation? If you want to make it go faster to that system, which number would you change? This one, right? Make it 0.3. All right? Let's see how that works. Nominator, denominator. It's called the transfer function block in Simulink. 0.3. Let's see what happens. All right. You see, it goes a lot faster to 0. Oh no, what happened? Which it doesn't work because you will have a steady state over here as well. See, it goes to 0.6 a lot faster now in about 20 seconds, right? In about 20 seconds. So let's see if our system can follow it now. Run. Tries to follow it, but now it has these oscillations in a little bit. Okay? So it basically says that you cannot follow this, you're going too fast. If you take this away, if you take the command filter away, like we did over here. This is the response. Sorry. Oh! That's what you meant. Crazy. Okay, I understand. Sorry. Okay. I need to put this to the. I put it into the same thing without into. Alright, so this was the response, 0.6, and let it run, and see what happens now. Well, it's approximately the same with the integral as well. But let's make it faster with the integral. Let's do a reference again. So we have the integral, which is a lot faster now with 0.3. And the integral doesn't care too much, because it's already looking at the integral area and it's slowing down and so forth. Okay? But if you go to this part, we have seen in the design that it can't really follow. Okay, so what we can do is we can make it 0.2. I think that would make it, this would work. It's a little bit better. Like 0.3, I think 0.1 was the easiest. Now you might ask what happens instead of giving a step input. What would happen if I would give, let's say, a sine wave? Right, what would happen then? Say run. And this is the sine wave. This is the input. Oops, not good. I mean, it is. I mean, of course, you know this is 100 seconds. Maybe I should do this only 30 seconds now. The whole run. I think better. Okay, this is how it looks like. Plus minus 0.2. Look at the response. Because it starts from 0, it's convergent with this. And your output will look like that. And that is because, of course, of your, but the number is very small. Okay? This is because your filter starts at, because the starting point, because there is a derivative over there, it needs to start at 0 and it goes up and all this. So you have to be a little bit careful with what you do when you play with these transfer functions. But I think you got the idea, right? You have to play around with it to get experience. Any questions?
If you interface, what's the sine input?
No such thing. The pilot will start doing this with your airplane to make the passengers sick. They did that to me. No, when the helicopter just said, okay, Ojam, what did you eat this morning? And I said, I don't care, you can do whatever you want. So they tried to make me sick. I enjoyed it, so it was of course it doesn't make any sense. But you have to also understand that this is a linear form. It's good for analysis purposes. You know, if you take 384, you will see frequency domain analysis. Frequency domain is how much you can, how much faster you can do this until it doesn't respond anymore. It's good for analysis. So, evaluation, see you on